All right, welcome back to TalkTensors. Today we're diving deep into something pretty crucial in medical AI.
Yeah, it's a paper called Evaluating Visual Explanations of Attention Maps for Transformer-Based Medical Imaging.
Right. And it's all about really understanding how these algorithms make decisions, which is obviously huge if AIs can actually help doctors.
Absolutely. The paper starts by laying out why this is so important right now.
Okay, yeah.
Like, we've got longer lifespans, aging populations, more demand on healthcare.
Right, it makes sense.
And AI could help ease that pressure. Vision transformers, or VITs, those are leading the way in analyzing medical images.
Oh yeah, VITs, we've talked about them before. They're really starting to challenge CNNs, right?
Exactly, even in medical imaging.
But the problem is, they can be kind of a black box. Like, how do they actually reach a diagnosis? Doctors need to know that to trust them.
That's the key issue.
And this paper zooms in on attention maps.
Okay.
They're like a core part of
Right.
VITs, right? And they could be a way to peek into their decision-making process.
Yeah, and there's actually a debate going on about whether attention maps really provide meaningful explanations.
Right.
Some researchers are optimistic, especially with self-supervised learning getting better.
Right.
They think these techniques might make attention more interpretable.
Interesting.
Others are more cautious. This paper jumps right into that debate, comparing attention maps to other explainability methods across like a bunch of different medical imaging problems.
Okay, so to really test these attention maps, they didn't just stick to one medical application, right?
No.
They used 4 different challenges.
They looked at identifying polyps from colonoscopies, detecting tumors in 3D breast MRI scans,
Got it.
and then telling the difference between a healthy esophagus and esophagitis,
Yeah.
and finally finding bone abnormalities like fractures in x-rays.
Wow, so they covered a lot of ground.
Oh yeah, and for each of those, they used large data sets to train their models
Okay.
and then really thoroughly evaluate how well we could understand the predictions.
To make sure the comparison was fair, they didn't just use one type of VIT either.
Right, they stuck with a standard VIT architecture.
Okay.
But they experimented with 4 ways of initializing those model weights.
Interesting.
So they looked at models trained from scratch. Those have random weights. Then models pre-trained on ImageNet, that huge data set, using supervised learning.
Right, that's pretty standard.
And then, this is the key part, models pre-train using 2 different self-supervised learning techniques, DINO and MAE.
Oh, right, those self-supervised methods. We've talked about them before. So by comparing all these, they could see how the initial training affects not just accuracy, but also those explanations, right?
Exactly.
Fascinating. Okay, so let's get into the methods they use to try to understand these models. First up, GradCam, right?
Yep.
I know some of our listeners might be familiar with that from earlier computer vision work.
Right, it was originally developed for CNNs.
Right, CNNs. And it basically uses gradients from the last layer's output to highlight the image regions that were most influential in the model's classification.
Exactly. It shows you what the model is paying attention to. And the researchers adapted GradCam to work with the final self-attention layer of their VITs.
Okay, makes sense. Then, of course, they looked at the attention maps themselves.
Right, which makes sense since we're talking about VITs. So the way VITs work is they break down the image into smaller patches, these little tokens.
Right.
And self-attention lets each token weigh the importance of every other token while it's processing that image.
So it's like each patch is learning which other patches are important.
Yeah, like they're learning to pay attention to the relevant parts of the image to make a decision. And those attention scores, that's what we're looking at for explanations.
Okay.
Specifically, the researchers focused on attention maps from the class token. That's in the final layer.
Right.
It's designed to put together all the info for classifying the whole image.
Got it. And then finally, they used a newer method designed specifically for transformers, right? The Sheffer method.
Yes. And this method looks at interpretability more broadly.
Okay.
It says just looking at the attention scores in that last layer might not be enough. You need the whole picture of how the model got to its decision.
So it's not just about where the model looked last.
Right. The Sheffer method takes both the gradients of the output and these relevance scores and sends them back through all the layers.
Okay.
It's like tracing the whole chain of thought.
Ah, that makes sense. To see how good these different explanation methods were, they used 2 quantitative metrics.
Yeah. The first is the pointing game.
Pointing game.
Yeah, so imagine an expert, like a doctor, has drawn a box around something important in the image, like a tumor.
Uh-huh.
The pointing game finds the pixel with the highest activation in the interpretability map. If that pixel is inside the expert's box, it's a hit.
Like it's pointing to the right spot.
Exactly. And the accuracy is just what percentage of the time it gets it right.
Makes sense. And the second metric was intersection over union, or IOU.
Right, IOU. That's more about the whole area the explanation highlights. So for each map, they take the top 5% of activated pixels and make a mask.
Got it.
Then they draw a box around that mask and calculate how much it overlaps with the expert's annotation.
Okay, so higher IOU means the model is focusing on the right overall area.
Yeah, exactly.
And the paper actually has a visual to show these two methods, which is helpful.
It is. Now, about the findings. First off, the VIT models were really accurate.
Okay.
They reached state-of-the-art or close to it across all 4 of those data sets.
That's important. We want to know that the models are actually good at their job.
Absolutely. But one thing they found is that those visual explanations can be tricky.
How so?
Well, sometimes a heat map or a tension map looks good, but it's not actually highlighting the important medical area.
Oh, so it can be misleading.
Yeah, and sometimes a map that's not as visually impressive is actually more accurate.
Huh. So you really need those objective metrics.
You do. And another interesting result was how pre-training affected the interpretability.
Okay, yeah, that makes sense. You're starting the model off differently.
Right. Even when models had similar accuracy, the explanations could be really different depending on how they were pre-trained.
Interesting.
So random weights, ImageNet pre-training, Dino, MAE, those all led to different results, especially with the attention maps. And self-supervised pre-training often helped, but not always, in the pointing game at least.
So it seems like self-supervision can make things more interpretable, but it's not a guarantee.
Yeah, there's nuance there, and it contrasts with some earlier work on Dino, especially with natural images.
Right, so the specifics matter.
They do. And another thing they found was that GradCam didn't do so well with VTs.
Oh, really? Not surprising, I guess, since it was made for CNNs.
Yeah, across the board, GradCam consistently scored lower than attention maps and the Sheffer method.
Interesting.
Which tells you need the right interpretability tool for the job. You can't just use anything.
So no GradCam for VTs, got it. But the most insightful part was probably the comparison between attention maps and the Sheffer method.
Right. Yeah, that was really interesting. So attention maps seem good at finding the most important spot in the image.
Okay.
They did well in the pointing game, but Sheffer was better at outlining the whole important region. It got better IOU scores.
So each has its strengths.
Exactly. And based on that, they suggest if you just need to find the one key spot, attention maps might be enough.
Makes sense.
But if you need to understand the whole area involved, Sheffer is probably better.
That's a good takeaway. But they also found a possible problem with how we evaluate these methods, didn't they?
Oh, yeah. They noticed that in some data sets, those expert bounding boxes were really big.
Okay.
And they might include areas that weren't actually part of the disease.
So they can make IOU scores look better than they really are.
Exactly. So they recommend using segmentation maps in the future.
What are those?
They provide more fine-grained annotations at the pixel level.
So you can be more precise in evaluating those explanations.
Right. And they said this could apply to pre-training too. It's not just about accuracy. It's about what the model learns to focus on. You might need to try different self-supervised methods to find the most interpretable features for your specific task.
So to sum up, VITs have potential in medical imaging, but understanding how they reason is still a big challenge. Attention maps are a good place to start. But this research shows they're not always the best. Transformer-specific methods, like the Sheffer method, often give you a better explanation. And we need to think carefully about how we evaluate these methods, moving beyond just bounding boxes.
Yeah, that's a great summary, and it's important to put this research in historical context.
Okay, let's do that.
People have been working on interpretability in machine learning for a long time.
Right.
Early models were simpler, easier to understand. Then deep learning came along, and things got much more complex.
Right, those multi-layered architectures are hard to untangle.
Exactly. And when attention mechanisms became popular in NLP, there was this hope that the same would happen in computer vision.
Okay, yeah.
Like with VITs, attention would just naturally make things interpretable.
Right.
But this paper shows it's not that straightforward. We need methods specifically for understanding how VITs work.
So things like GradCam, but for transformers.
Yeah. And that's where methods like the Sheffer method come in.
And self-supervised learning is playing a role here too, right?
Oh, absolutely. The idea is, by training models on lots of unlabeled data, you might get more interpretable features,
Right.
including the attention maps. And this paper does show some evidence for that, but it depends on the method and the task.
So self-supervision might be part of the solution, but it's not the whole story.
Right. And it raises another question. Can we design pre-training methods that actually boost explainability?
Even if accuracy takes a small hit.
Exactly. That's something to think about.
Okay, so big picture. This paper did a few key things. It compared those different explanation methods for VITs in medical imaging, GradCam, attention maps, and the Sheffer method.
Yep.
It showed how different pre-training strategies affect interpretability.
Right.
And it pointed out some problems with how we evaluate interpretability, especially with bounding boxes.
It really moves the field forward.
Yeah.
And practically speaking, this research is important for getting doctors to trust AI.
Right. Trust is everything in medicine.
And better interpretability helps with that. Plus, if we can see why a model makes a prediction, we can spot biases and potential problems.
That's crucial for patient safety.
Exactly. Imagine if an AI flags something suspicious, but it's actually focused on something irrelevant.
Right. We need to be able to catch that.
And this isn't just about safety and trust, it's also about helping medical researchers.
Okay, how so?
If we know what parts of the image the model is using, it could lead to new discoveries about diseases.
Oh, like new biomarkers or something.
Exactly. And when AI in medicine faces more regulations, strong interpretability will be key.
Right, to show these systems are safe and effective. So let's move on to our novel notion segment.
Right.
One thing I was thinking about is, what if we combine the strengths of different methods? Like attention maps are good for location, and Sheffer is good for overall relevance.
Yeah, that's a cool idea. A hybrid approach.
Right, you could use attention maps first, then Sheffer to give more detail.
Or the other way around, depending on how confident the model is in its prediction.
Exactly. Maybe you could even use meta-learning to train a system to pick the best method.
That would be amazing.
Another thought I had was, what about the stability of attention maps?
Stability.
Like, how much do they change if you slightly alter the input image? Or if you compare different models trained on the same data?
I see what you mean. So if the attention map is all over the place, maybe the model is relying on something unreliable.
Exactly. Even if it happens to get the right answer on that one image.
That makes sense. We could develop metrics to measure that stability.
Right. And see if it relates to how well the model generalizes to new data.
And how reliable it is clinically. Maybe you could even use that to design new training techniques that encourage stability.
That would be really cool.
Yeah, if a stable attention map meant a more reliable model, that would be huge for doctors.
Absolutely. Of course, this is all just speculation, but it shows how much there is to explore.
There's so much potential in this area.
Okay, so wrapping up this deep dive, the key takeaway is that even though VITs have attention mechanisms, that doesn't automatically make them interpretable. For something as important as medical diagnosis, we need to really test our methods and be open to new ideas.
Absolutely.
And we need to be careful about how we evaluate those methods too.
Right, it's not as simple as just using bounding boxes.
And for anyone who wants to dig deeper, you can find a link to the paper in the show notes. Thanks for joining us on TalkTensors.